yours.
Thank you very much, Natalie, and welcome everyone to the webinar on 3D printed electronic motors for microdrones. First of all, I want to talk about nanodimension, that is focused on true Industry 4.0 solutions with different 3D printing technologies for additive manufacturing, going from assembly of electronics, ceramics, and metal printing, micropolymer, and the star of today, the DragonFly 4, that is the additive manufacturing 3D printer for electronic circuits, printed circuit boards. From this division on nanodimension has been focusing on all these Industry 4.0 and the most difficult structures to make. And then 3D printing for electronics is one of those. So in order to explain this technology for all of those that don't know much about the DragonFly, I want to go to the generalities of 3D printing. The most popular is extrusion printing, that we have machines like the Bamboo Labs Reality that we can get on Amazon for home usage, that they have a filament to make printing plastic objects. There are industrial versions that use this material through extruder heating up, and this polymer can get into different shapes. But it still is kind of the most accessible and also the least powerful technology. There are other technologies like selective laser sintering, in which a laser objective is focusing a beam onto a powder bed, mostly for metals, and it's possible to 3D print metallic features. Another one that is very popular is stereolithography, with or without projection. There are also affordable machines that has an LCD display for making the UV light passing through an image, making a photosensitive polymer to adopt the shapes layer by layer, and the most precise, like the Fabrica from the nanodimension, that uses a projection system and makes features in range of microns. But the last one that I would focus, because this is the one from DragonFly, is inkjet printing, and we use printhead just like the paper color printer and inkjet, in which we deposit droplets of a material. Instead of a color pigment, we will use polymers to get the material conductive and dielectric with two different printheads. So it's probably faster and easier to see it in a video. The machine is around about 2 meters by 1 meter by 2 meter tall. We have two materials, one conductive and one dielectric material. We call them inks. We get first the conductive material. And this solution is based on silver nanoparticles. It's enclosing a solvent. The solvent will evaporate, and we will sinter and bond the materials with infrared radiation. Afterwards, the electric material will be jet with a different printhead and will be cured with UV light. And we will repeat this process layer by layer. Each layer is 1.25 micron thick, in which we are depositing these droplets. And the way to go and make this, we start from a back profile, like a Gerber or ODB++ from circuit board industry, but also STLs from the 3D MCAD design. We need to command the printhead, so we make a digital file that is basically an image that tells the printhead where to fire these pixels. And this will make one image for conductive and one image for dielectric, and we command the printer to jet those materials and making a process that cures them and solidifies them in a very homogeneous way, achieving these kind of structures. Here we can see a cross-section of a 3D printed circuit board with different features, different thicknesses of metal. Here we see in the middle a through-hole via with several different layers in a PCB stack up. And on the right, we see stagger vias, that they are not needed but the designer wanted to make it that way, because with 1.25 micron resolution in z-axis, we can basically make 45-degree interconnects if we want to. So the idea is to go from a layer by layer solution to a true 3D printed one, in which we can even embed components by pause the printer in the moment it creates the cavity, insert the component, and resume the print and complete the structure, or even take the partial structure out to a pick and place machine like the SNTech box, jet and dispense solder paste or conductive glue, also based in nanoparticles, cure the bonding glue, and come back to the printer to finish the encapsulation. So we get flexibility in the customization, making waveguides, true twisted pairs, and vias in any shape. Coils, we have here a 45-degree interconnect that is basically a via, but we don't have a drill that makes these connections. So why trying to mimic the same structure if we can make them with bigger performance? Also, because of the resolution in 1.25 micron, we can also create capacitors and make a structure with more than 55 layers on the circuit board. Adding layers is almost for free, it's not a cost incremental process in this technology. So we play with those in order to get the bigger performance required. And this opens a different world, and the most important is to start thinking outside of the box, because we need to design in different ways. We need to design with MCAD and ECAD at the same time. We need to think in the design of the system in 3D and how the performance will affect in the three-dimensional space, and how can we use this extra axis of freedom and not just having kind of a 2.5D design and just adding much more layers like in the normal regular process. And also it's very important to mention that the traditional manufacturing has a lot of chemicals involved, and with this technology we reduce 99% of the waste. We have no usage of water, and because of this small electricity consumption, also we reduce the CO footprint and the chemicals usage, because we only have a glycol-based kind of solvent to keep the printing heads clean, but that's it. The material we need for a circuit, we add it as we need it without any waste, and we don't have a post-processing on the 3D printed parts. So after describing what the technology entitles, let's go to the topic that is using additive manufacturing electronics on UAV applications, or also commonly known as drones. So the drone term is broader, that includes robots that can go on ground, on water, and the UAVs are the ones that fly. So focusing here, if we use AME in drones, we obtain design freedom because we can start using the 3D space to customize the builds and to meet specific design requirements. One of the easiest one is to create very small parts, or to create very small flying machines, because we can have certain control in the three-dimensional space and increase density. We shorten the design cycle because we have a machine that prints in-house, so we don't need to wait for several weeks until we get the complete part built. We can just print it overnight and start assembling tomorrow. We reduce the assembly time and effort also because we can integrate several different parts in the same print, the mechanical with the electronics, and not starting screwing a lot of mini parts. And this also can improve the performance because integrating conductive geometries within the drone structure can reduce electromagnetic interference. Or we can even go clever and reverse the electromagnetic behavior by using metamaterial structures, and this can improve the overall performance. And we can even potentially add stealth capabilities with these kind of metamaterials in the scheme of the structure, just by adding the mixture of conductive and metal resonators. So to go on the basis for every flying machine, for the drones, we need to generate lift by the airflow that goes with the sheet made by the rotor blades. We have a specific blade design that all the blades that we can just buy the blades or pre-print them will require to go on the shape. But this is something we can get from any book or even download the 3D models. After making the lift, we need to generate thrust with the motor, that is the forward force that propels the drone. If we go just into a quadcopter, we can control by balancing two different directions, as in the picture. There is also drag and the resistance force opposing to the drone's motion, and with the aerodynamic that we can make on the shape, also 3D printing, we can increase the performance of these, but also we can reduce weight by only printing the structure we need and not more than that, not having more frame than the required. And also the weight that is making the autonomy of the drone reduced, because we have certain power that can be given by the batteries, and the weight will be a major player in this. So any flying structure we want to make it the lightest possible, because this will give us the autonomy required. Otherwise, we get to designs that are very nice, but they can only fly for a couple of minutes, and then they even need a higher capacity battery that is also going to be heavier. So the easiest way is to just go on lighter structures in every single part of an aircraft. From types, because there are different types of drones, we start from the most oldest design, that is fixed wings, that resemble an airplane design with only one rotor. We have single rotor that resemble an helicopter, but we need a rotor for thrust, but another one for control. And we can go in the multi-rotor, starting with 4, that is the easiest to control, to even hexacopter or octacopters that can give more performance. Or we can use a combination of fixed wing and rotors, like the IRID vertical takeoff and landing aircraft. They are kind of the best of both worlds, but also the hardest to design for the drag and the aerodynamics. So now, because we want to make a demonstrator, we want to show you a simple design. A quadcopter is kind of the easiest to control, and also there is a lot of open source work we can leverage from. So in general, quadcopters are mechanically very simple, and that's the beauty of it. They consist of a frame that holds all components, mechanical ones, a flight controller that is going to be the brain, the CPU, that will include the flight control loads in order to compensate the flight. We need an RF transceiver to give commands from a remote control. We need, of course, the motors that will be connected to the propellers. And these motors will need to be driven by speed controllers. And we need a power stage with batteries. And after having something that flies, possibly we want to have first-person view equipment, like a camera mounted, and a nice transmission link to the FPV viewer. So in Nano Dimension, we started with the idea of drones since a few years ago. Our partner James started doing the first axial flux motor with the idea to reuse it for drones. And they also did a very interesting design that was resembling the shape of a drone, but was more like the demonstrator to have the speed controllers for these motors in the shape of a drone. They actually did a drone, but making it with AME required a lot of resources in order to make a very nice product. This one was too big to start with. So later on, here in Nano Dimension, we started with a Microdrone, trying to be the lightest way possible, the simplest possible, and trying to just make the minimal components we need to fly. So because of that reason, the camera is not present in the design, but that doesn't mean you cannot add a camera. So this quadcopter is just 60 by 60 millimeter. It's very small. You can put it in the palm of your hand. It's using brush DC motors in order to make it just simple, motors that just move in the right speed and make enough thrust. The mechanical frame is completely printed with the PCB, and for the 3D print of this model with the DragonFly, it takes 12 hours and uses only 1.4 milliliters of metal conductive ink and 6.6 milliliter of dielectric. If we think in these spoons for medicine, well, this is just a spoon for baby medicine of dielectric, and less than half of this spoon, a third of the spoon for the conductive metal. It's a very small amount of materials, and this is also part of the beauty here. The design, the system is very lightweight because we are not using a lot of material. We are not removing it. We are just adding what we need. And because of that, we took the decision to go in this way. In order to make the flight control, the minimum amount of things we need is a microcontroller that has an RF transmitter. If it's not integrated, we can add it to any of the GPIOs, but this one had an integrated RF transmitter and was based on an ARM M0 system on chip. We need two sensors that are the very minimum, an inertial one in order to give the drone the sense of position, and an air pressure sensor in order to give the compensation on the flight and the altitude, how high is flying or low. And from this is all enough for the sensors. We only need to drive the motors with speed controllers. If we go with brush DC motors, they are very simple. You only need a MOSFET to drive them to give enough power from the batteries, and just driving this with a pulse width modulation from the microcontroller. So 4 channels of independent PWM are good enough, and to give to an open source control software like Betaflight, and the software is going to connect everything beautifully because it's the contribution of several developers. And for the power stage, it just uses one lithium polymer battery. The microcontroller works in the range of 3.7 to 5 volts, so it doesn't even need a power regulator. Everything works nicely connected to the microcontroller and the battery, and that's it. An LED for indication that everything is alive and is receiving commands, and that's it. A remote that comes off the shelf controls this part. It's more interesting to see the mechanics of this because it's just a simple design made with art to reduce cracks and impact. Of course, in a flying machine, we will have impact. The first one is that by having no power, and then it just crashes on the ground, but also on a command that can make a forbidden flip, and then it crashes on the wall. So we try to minimize this by printing this kind of art design, just holding the motors in place, but adding also the circuit board to the same mechanical frame. So this is just one print, includes all the circuit board, and after printing, you just push the motors in position after soldering the components, and stick the battery with double-sided tape. So it goes with the simplicity of reducing weight and adding only the important parts. The most important thing in this design is to have the inertial sensor at the center of gravity, so all the weight is balanced, and in the complete center position we have this sensor, and that's what we need. All the sensors are connected by a square S, so it's just about to have a nice, simple design and interconnect. Now, for design considerations, because we are not using a PCB, a normal manufacturing of circuit board, but we are using TME, we only need 2 layers to make this kind of design, but we have many layers that are for free, so we can remove the ground and power and make them in 2 independent layers, and it's a 4-layer design that costs the same For designing this, but we just add these 2 layers. It's okay, and we reduce also the density because we don't need to have area for this interface. And then because we also want this part to behave the most balanced possible, also in the assembly, we don't want any warpers, because if it warps during assembly, afterwards the part will be mechanically more prone to cracks. So we reduce the warpers by duplicating layers. We make dummy layers of each one of the layers to make balancing in the Z-axis, because we can just duplicate layers in the slicing tool in the machine software, and these layers are not connected, they are just dummy, they are there, but they balance thermally the assembly when we go into a refill oven. So it's a very simple and clever way to make this balancing. And for AME, we have consideration in 2D that goes like the minimum trace width is 75 micron and the minimum spacing is 100 micron if we make everything in a flat design, a flat area. The moment we start going on Z-axis, we have vias of minimum 150 micron and through holes of minimum 400 micron. Because when we are stacking metal material or making like a pyramid, we want the column to not be in a ratio of diameter and height ratio so thin because it can collapse. So we have these guidelines to increase the yield in the manufacturing, but also for this design, there is no need to challenge these guidelines. Really, we don't need to just go on the absolute minimum because the machine can do that, because that will translate in a lower yield in any manufacturing technology, including this one. So because of that, we don't need to exert these limits. We use 100 micron traces at the minimum. We try to make them bigger as possible. We used also a minimum 150 micron spacing. We made mesh in power and ground layers because that also makes a good thermal balance and compensation, reducing warpage. When we make a circuit board, we also have warpage because of metal imbalance. But on AME, we are adding the polymer, and we don't have the fiberglass reinforcement that is basically the definition of FR4. So here, if we will experiment a warpage that we have it by design, then we will have this warpage by at least twice or maybe 5 times a bigger effect. But we can reduce it by design in this way. Because additive layers really didn't cost neither time or just a little extra material, but we are challenging the 1.6 millimeters for this 8-layer print, 6 milliliters for this 8-layer print, then it's really a no-brainer to just do this compensation by design and make a smooth, high-yield manufacturing for this design. And the metal thickness is also 35 micron. We have a maximum of 100 micron. We don't need to go to the limit. So the test flight of this, here is the assembly of the part without motors. Then we added the motors. We could have made the motors to wire into the frame, but for the prototype, we didn't do that because if it cracks in the first crash, then you have no drone. If you have wires, then it's simpler that you can crack the frame and you can just reprint it easily without reprinting everything, just fixing the wing that is broken. Some super glue and you're good to go. But it can be completely printed, the wires, the motors, and you can make many optimizations on your product. This one, the idea was to just go on shows and be used by everyone. And if it's broken, then no big deal, we can fix it easily. So one flew very nicely. And see, the control is kind of simple. We tried not to make some flips because we didn't want to just break them. Takes 12 hours to print, so yeah, we have a big queue for printers, so we don't want to just break them for the sake of breaking. And then the next iteration, now that we made a drone to fly, well, it used brushed DC motors. Can we design a motor for it? Yes, of course. So we wanted to replace these ones with a 3D printed one, Axial flux. This one has two different stators and one rotor in the middle with 6 coils per stator. So we can see here, 1, 2, 3, 4, 5, 6. And make magnets in the rotor to have this imbalance. But because we are duplicating the stators, we can just shift by 90 degrees and increase the magnetic flux that we will exert in these electromagnets. In this way, we can increase the speed. So we are pursuing for the highest thrust on this model. Here is a cross-section of it. We have a stator with a 10 millimeter diameter. The motor is super tiny, just 1 centimeter. And the thickness of the circuit board is 1.57 millimeter thick. But it has 16 layer equivalent to a PCB that they are with 30 micron conductive layers. We embedded a ball bearing of 3 millimeters by 1 millimeter in order to insert a shaft that will hold the rotor with the magnets. The rotor is printed with a polymer 3D printer. Here the Fabrica that we have here in another dimension. And yeah, it's just a matter of assembling the rotor with the stator. We use the 0.5-inch pins in order to go to these vias and make the interconnects from top to bottom easily. And this can land on the arm, on the circuit board arm of the drone with these pins. So it was designed for simplicity. But also in the design considerations that we didn't want to exert the maximum limits. We know for sure that we have through-hole vias for 400 microns. We have a mesh spacing of 500 microns. So this design is very tiny, but if we play with these values, then we get a very, very nice sharp print with all the features we want without reducing quality or G. And also because of the amount of metal we are using and the big coil mechanical structures, we needed to go with a minimum thickness of dielectric of 75 micron as recommended by the design rules. Not the 10 micron that is the minimum, because thermally we will have a disaster when we start making a lot of metal layers without the right spacing on dielectric. So the results are here. The 3D print looks very nice. This is 1 centimeter diameter. We can see 3 millimeters in the inside. Every single coil, everything is very sharp. They measure 2.5 ohms individually. They are connected from the left to the right side, each one of them, and then we stack them together, the bottom and the top one, doing this trick. One via is connected to this one, the other one is not connected, because when we shift the other design, this one is going to be the interconnect from top to bottom to the other stator. So on the circuit board, each one of them will control the different coils. The odd pins will control one stator, and the even pins will control the top stator. Then we did the first test. The first test was just did a week ago. We just powered the motor with 5 volts. It consumed 150 milliamps. We noticed that because of size, we need to optimize the speed controller. We took an off-the-shelf one, but we need to play with the frequency that we cannot adjust in one of these off-the-shelf controllers in order to find the sweet spots for the rotation. So this is part of the future work. To conclude, using AME on 3D printed drone applications enables the creation of highly customized, lightweight, and integrated components. We push the boundaries of what we want in a flying drone design. We may have a potential impact in the industry by quickly prototype and tailor the component we need for aerospace using AME technology. It gives unprecedented flexibility, allowing for quick adaptation to specific industrial needs. And also, if something breaks, you can 3D print fast and overnight, and you have your supplies tomorrow. In the Innovation Drive, we illustrate with this project how the innovation materials and manufacturing process give us advancements in this drone technology. And the future directions, we made this design to showcase the electromechanical capabilities that we can give with AME with the DragonFly 4. There is a lot to optimize according to a specific task. We didn't have a specific task. We only want to make a demonstrator that showcase that we can make a circuit board to fly. And if you get the DragonFly 4, it's just about assigning resources to get there. So with this one, we get to the finish of our presentation. And now is the time for the Q&A.
Thank you, Dr. Rafael Del Ray. I just wanted to point out, someone mentioned in the chat that if you are using your mouse cursor, that they cannot see what you're pointing at within the presentation. So just as an FYI. But it was an excellent presentation, really insightful, exciting. I think this is where the future is heading. We did get some questions in, and I want to encourage everyone who has questions, please use the Q&A button to post any questions that you may have. I will go ahead and start with the first one. So the first question is flexible printed circuit used as a technology for printing?
The answer is yes, it's possible, because this polymer, if you print features of less than 250 micron, the polymer behaves flexible. It's not flexible as Kapton, that you can make a very, very narrow angle of flexion. However, it's good enough that we have tested 100,000 stress flexures with a diameter of around 2 centimeters, and it was good enough in that way.
Okay, I hope that was satisfactory. Then the next question is, what is the time difference of manufacture compared to traditional methods? What is the cost difference? I know this is very hard to dive into, because it really depends on the application itself, but if you could give a general answer, that'd be great.
Yeah, we can make a full session answering this question. So in order to go short, any 3D printing takes time. So we take 12 hours to print 1-2 parts. The traditional manufacturing is optimized for printing hundreds or thousands of parts per minute, but they are making a lot of waste, and you need to make a lot of NREs, non-returnable expenses, in making a stencil, making fixtures, in order to have everything for the different production steps. If you go to prototyping, you need to make a huge effort to manufacturing a few prototypes, and this is the biggest advantage, that you can just 3D print and in 24, 48 hours having your concept built, and you need to wait a few weeks for 1 part or 1,000 in the normal manufacturing. So in prototyping, yes, it's faster and cheaper, of course, but it's not meant for mass production of larger parts. If we can consider mass production of very complex parts that are very tiny, yes, of course, because we can set 100 parts in the printing bed. The maximum printing bed for the DragonFly is 160 by 160 millimeters, so I'm talking about clockwork kind of dimensions. Something like a full printed drone is not going to be the best idea for mass manufacturing if you need something like mobile phone volume. But if it's just aerospace volume, then it's quite okay.
Yeah. Okay, I think the next two questions, I'm going to combine them, and they're pretty much just based on the previous question of what are the benefits for using AM or AME in this case. So the questions combined are, what are the different print durations for the specific rotor design and the electronics board in comparison, and why would you want to use AME compared to traditional manufacturing methods for motors of a similar size?
Well, first one is the assembly. You don't need to wire the coils by hand. If you are making a prototype, You can just click and print your coils, and the coils are printed perfect. And then you assemble all the remaining parts. If you make all the jigs and fixtures to make your coils, then that's a different story. But usually, if you are just prototyping coils in your motor, then you really want to not waste time on this. So here is the advantage in the prototype stage. In the 3D space, and if you play with geometries and start making very powerful coils with a lot of layers with the freedom of space, you can also make them very dense. And the mixture of dielectric and conductive, you can not just make coils for a circuit board that are planar, you can make something in between that they are the coils in 3D space. But of course, just making coils by wire will have different properties. Let's say that is, I cannot say this is better or the other is better. It's just a different way, and according to the creativity of the design, it can be a better solution.
Yeah. Just because we're running out of time, I'm going to stick to 2 more questions. So one is, when you state that the bearings are embedded by gluing, could you please describe this further? That would be the first one. And then the last question is, what are the design tools for layout of the PCB?
Okay. The design is a donut, and at the end of the design, we just 3D printed a fixture to align the bearings, and that's super glued to it. They can be part of the printing process, but because of the mechanical super tiny bearings, we didn't want to get them into the heated system of the DragonFly. But parts can be inserted mid-print. So that was kind of the idea, but we didn't want to risk this. So we just make the donut and a fixture to fix the bearings position and use super glue. And it worked very nicely because we want the bearings to reduce friction. So this super glue is not causing any kind of stress. And the other question about the tools used for that, for ECAD, it was used Cadence Allegro. And for MCAD, Fusion 360. And we have a Fly Hub suite that you can merge the mechanical and the electrical ECAD designs both together. And this is part of the strength we're trying to go with the full solution.
Okay. Well, I pretty much thank you for your time today. It was very insightful. It was a great webinar. Anyone who has additional questions, please do not hesitate to reach out to us. You can always contact us at sales@nanodi.com or go to our website page and just fill out the contact us form, and we'll be happy to follow up and answer any questions you may have about the process, about our technology, or just to get in contact with Dr. Rafael Del Ray personally. And on this note, thank you everyone for your time, and I hope you have a wonderful day.